Alright, for 3.3, after some deliberation in class and after working on a lot of the homework for this particular section, I realized that just paper notes are not going to be quite enough to make sure that you understand and grasp all of the material we're covering here. So we're going to go ahead and look at a little bit of a video presentation. Right? It is important to note that position time graphs of accelerated motion are not linear. We are looking at the fact that we have a parabolic curve. Well, what does that look like? If I were to go ahead and sketch my graph, I have my axes, my position axes, my time axes. Right? Pardon my shorthand that I don't exactly use on the board, my position and time. I'm going to see a curve much like this one. Right? The sign of our acceleration does determine if our curve is up or down. Right? The curve I've drawn here is positive because it's up. If I have a negative acceleration, we're going to see down. If I have no acceleration, then I am going to see the lines that we are most familiar with on a position time graph. Right? And in that case, I am going to see an entirely straight line. Right? So we are looking at this one is acceleration is positive or greater than 0. This one here is acceleration is equal to 0. And this one down here finally is acceleration is less than 0 or negative. Right? The next thing we are looking at is the fact that the magnitude of curvature is determined by A, as in the acceleration. What I mean by that is the fact that the larger A is, the steeper that curve. I can go ahead and draw my axes again, or my, or my position and time. If I have a very large A, I'm going to see a very steep curve like this. If I have a less large, I'm going to see a much gentler curve, and I can see very drawn out curves. Alright? And this one we are looking at here to the left is going to be a larger magnitude than this one here out to the right. Right? The next thing we are looking at is the equations. We did see position versus time equations where we saw that I apologize. Alright. We did see the fact that this was my dependent variable. Right? This is my y-intercept. This term is my slope. And then finally, this term here is my independent variable. All right, and that did give us the graphs, like I said before, that we are most familiar with. We had our axes. I have my position versus time. And I am looking at the graph of a straight line. Right? The slope of this graph is our velocity, and where that gray line crosses my x-axis or my position axis or my y-axis is my y-intercept. Where did I actually start? Now we're going to look at it a little bit differently. We're going to go ahead and look at our little bit more complicated version. All right, we're still going to look at the fact that xf is our dependent variable. All right, xi is our y-intercept. All right, vi does still have to do with the slope. It is our initial slope. Alright, then we can go ahead and the fact that A is how much curve we have. Right. T in both the second and the third term are still our independent variable. This whole last term is what gives the equation its curve. Alright, so we can go ahead and look at that in the graph like we were before. I have my position axis, I have my time axis. Alright, but instead of a straight line, we have this curve. Right? We are still going to see that our y-intercept is where that line crosses the axis. Right down here. We have our initial slope, what the slope we begin at, and how curvy our line is. Right. The next thing we are looking at is the fact that position time graphs can track multiple objects. We're already a little familiar with this. We've talked about this previously in class because guess what? We've done it. When we were looking at the constant velocity cars, we went ahead and looked at our graph. Right, and we actually saw multiple objects graphed on that. We can look at one with, let's go ahead and look at one with a constant positive velocity. We can look at one with a constant negative velocity. We can even look at one with a small positive acceleration. We can look at one with a large negative acceleration. Alright, so we can look at more than one object. We can see how they interact. We can see how they compare to one another and all that fun stuff. Alright, we're going to go ahead and work through an example problem. We are looking at the fact that a speeder travels at 18.2 meters per second. The instant our speeder passes a parked police car, the police begin their pursuit with an acceleration of 4.5 meters per second squared. Our speeder maintains a constant velocity. We want to show that the police car catches up with our speeder after 8.9 seconds. We want to determine the location where this occurs. Well, to do this, what we're going to do is first of all build an equation for each car. Right? Once we do that, we're going to go ahead and plug the time that we've been given, right? And we will get a position. Hopefully, if everything goes well, we get the same position, right? That tells us the location where the police car catches up with the speeder and shows us that we are catching the speeder at 8.09 seconds. So, when we go ahead and look at our equation for our speeder, right? If we look at our equation, look at building in an equation for our speeder, we are dealing with the fact that he is moving at a velocity of 18.2 meters per second. This is a constant velocity. That means our acceleration is equal to 0. Right? The next thing we're looking at is we're starting our picture where both cars are occupying the same space at the same time to begin with. Right? We're going to go ahead and set our initial position to 0 as a result. This is going to be true for both cars. Right? We have our speed, we have our acceleration, we have our initial position is equal to 0. We can go ahead and build our equation from here. We are going to go ahead and pull the very standard equation number 5 from the 3.2 notes, and we are looking at the fact that final position is equal to initial position plus VIT plus 1/2 AT squared. Alright, one thing to consider though, however, is the fact that we do not have acceleration, so this last term here does go away. Alright, so we can go ahead and plug in our 0 for our initial position, plug in our velocity of 18.2 meters per second, and we do end up with the equation of our position is equal to 18.2 meters per second times t. This is our setup equation for our speeder. Before we go ahead and find out what position our speeder is at 8.09 seconds, I'm going to go ahead and draft my equation for my police officer. Alright, when I go ahead and draft my equation for my police officer, alright, I am seeing the fact that he's starting from rest. He's initially parked, so my initial velocity here is going to be 0. Alright, we also established the fact that they will have the same initial position of 0 meters. Alright, we also have the fact that his acceleration is 4.5 meters per second squared. We do have everything at this point to go ahead and pull the information for our equation, and we are, like I said before, using that fifth equation. XF is equal to XI plus VIT plus 1/2 AT squared. Like I said before, our initial position is 0 and our initial velocity is 0, so we will zero out those two terms. So when I go ahead and plug in all the rest of my information, my XF is equal to 1/2 times my 4.5 times my t squared. Alright, now I have both sets of equations, and I can go ahead and start plugging and chugging to verify that my numbers are the same. Alright, so I'm going to go ahead and start by plugging in with my speeder. My final position is equal to 18.2 meters per second times 8.09 seconds. When I do put that into my calculator, I do get 147 meters. Right? Like I said, if everything goes well, we should get the same sort of information for our police officer. XF is equal to my 1/2. Actually, I'm going to go ahead and simplify that. My 2.25 times 8.0. Hold on, running out of space. Try this again. meters per second squared times 8.09 seconds squared. It is important to remember that this squared here, this last one that I put in, is just for the time. When I'm looking at the fact that I have meters per second squared, that per second squared is just the unit. It doesn't have any bearing on what's going on mathematically. It's just to make sure that you're accomplishing your dimensional analysis and nothing else is going wrong. Alright, when I go ahead and plug that in the calculator, everything did go right, and I do get 147 meters. Alright, so things have suddenly changed. What we're going to look at is looking at this exact same problem in a slightly different format. If I had not asked you, if I had not given you the time in order to verify, we can go ahead and build the equations and find out at what time and what location they meet. Algebraically, you would do this by setting your two equations you created equal to each other. All right? That would let you solve for time. After that point, you can then go ahead and plug that time into either equation that would give you the position. I'm going to show you a slightly different version. When I go into my calculator, all right, I can go ahead and plug my information in. If I go ahead and put in my equation for my speeder, I have 18.2, my velocity multiplied by my independent variable. My independent variable is usually x on a calculator, even though we called it t in our math. So I'm going to go ahead and put that in there. And then I'm going to put in my equation for my cup, which was my 2.25 times my independent variable squared. So those are my two equations, and I can go ahead and hit graph. Alright, chances are when you graph this, you're like, whoa, I can't see anything. This doesn't make any sense. Alright, I can't do anything with this information. So we're going to go ahead and readjust our window. To do this, we're going to hit the zoom button, and when we do that, we can scroll all the way down to 0. Zoom fit is going to give us a nice window that'll have our information that we care about inside of it. Alright, so there's our graph data. Alright, and we're going to find out at what point do they meet. Alright, so to do that, I'm going to go ahead and hit the second button on my calculator, and then I'm going to hit the trace button. Alright, you'll notice above the trace button does say calc. When I click on that, it does give me a lot of different options. I want to know at what point do they intersect, which is option number 5, and I'm going to go ahead and click on that. At this point, it gives you first curve, which is where are you looking at, what is your first line. Alright, you do want to get your cursor or your information close to where your intersection is, just to help speed the process along. So I get that up close to where their first curve is, get the second curve up in that area and hit enter, and your guess somewhere in that vicinity. Alright, my calculator does a little bit of thinking, and then it realizes that I do have an intersection at 8.09 and 147. Remember, our position was our dependent variable, which was on our y-axis, and our time was our independent variable, which we graphed on our x-axis. Well, that goes ahead and verifies everything that we went ahead and found out. Right? Because you can see that we have our position. This is our time of 8.09 seconds, and we even have our position, of 147 meters, just like we expected. Alright, I did have one last thing I wanted to cover, and the fact that we have that graphs can show both acceleration and deceleration. Right? One thing I do want to point out is how much I loathe the word deceleration. It's not a good descriptor of what's going on, right? Because we can have an object accelerating but still speeding up and slowing down. All right. In this case of this particular graph, I do have a constant acceleration. My constant acceleration is downward. Right? But I have a very nice clear curve on my graph that will show my object first slowing down and then speeding up. And I can look at that. We find out the slope of this by actually using what is called the tangent line. We won't have to do a whole lot with that, but we do need to have a brief idea of what's going on with the tangent line. A tangent line from math, as you may remember, is a line that just sort of touches in one spot your curve, and we can find out all the different information going on from our picture with the tangent line. All right. So I can see at the beginning I have a tangent line here, and it's going to grow less steep and less steep. All right, and because that slope is of the pink line, all right, is getting smaller and smaller, or the slope of the pieces of pink line are getting smaller and smaller, I can see the fact that my object is slowing down. But once I round the top of the curve, by the way, the very top of the curve, that flat line, is my speed is equal to 0. Once I round the top of the curve, my slope begins to increase in magnitude. And as it begins to increase in magnitude, we can actually see the fact that our object is speeding up. Alright, that's all for Chapter 3.3. Please go ahead and start working on the Chapter 3 Part 3 homework and let me know if you have any questions.